Good morning, sir. This is the EL for Advanced Energy Storage Devices for E-Mobility. Our paper title is Bio-Inspired Electrode Architecture for High Energy Density Batteries. I'm Rohan.
I'm Bilal.
I'm Sanju HK.
Yeah, let's see what are the problems with the conventional electrodes. The first thing is they are not stable. First thing is mechanical instability. Traditional electrodes made of randomly packed active metals which suffer mechanical failure during repeated charge discharge cycles. This causes electrode degradation and volume expansion. The second thing is limited ion diffusion and electron transport. The lack of structural optimization leads to uneven lithiation, delithiation, and this occurs and hence reduced electrochemical efficiency takes place. The third problem with the conventional electrode is poor electrolyte penetration. The flat and bulk electrodes do not support hierarchical porosity, hence slow reaction kinetics happens, hence low power density takes place. Let's see what are the bio-inspired solution for these conventional electrodes. The bio-inspired are nothing but inspired by nature's designs, like structures like bone, wood, leaf, veins, and honeycomb, which possesses hierarchical porosity, mechanical robustness, efficient transport channels. The advantages of these are it has enhanced ion and electron transport. It accommodates volume changes, which turns into a long life. Then it increases energy and power density. Then greater electrolyte accessibility and flexibility. Hence, we can say that by using bio-inspired electrodes, which mimic nature's efficiency to overcome the limitations of traditional designs, opening avenues for the next generation high energy density batteries. Let's see what are the principles behind these structures which are inspired by nature. The first one is honeycomb structures. The honeycomb pattern of repeating hexagonal cells, well known for its lightweight, vast surface area, and high mechanical stiffness. This is used to create electrodes with high active material loading, allows fast ion electron transport, provides structural integrity under stress, improves electrolyte access and diffusion. The second material is wood and bone. Wood has a complex network of capillaries, hence, and bone has a porous matrix of osteons and canaliculi. This create multi-scale porous designs, mimic macro, meso, and micropores. These are components of the wood and bone, enable fast ion diffusion and mechanical flexibility, reduce damage from volume changes during battery cycling. Third material is leafy veins. As we can see, the leafy veins from the vascular systems of plants and trees, their branching nature inspires electrode designs that permit uniform charge transfer. These provide continuous ion conducting channels, uniformity and in ion transport, minimize the ionic resistance, enhance cycle life and rate performance. These are the hierarchical porosity in the electrodes. Hierarchical porosity refers to the presence of pores ranging from nano to micro scale within a single electrode structure. This includes three types of pores. The first one is macropores, which has greater than 50 nanometer of size. These serve as a reservoir and highways for electrolyte invasion and bulk ion transit. This reduces diffusion resistance, help during high rate discharge. The second one is mesopore. This provide additional surface area for electrochemical reactions and serve as an intermediate ion diffusion pathways. This increases electrochemical activity and hence support ion transport to deeper layers. The third one is micropores, which has less than 2 nanometer of size. Due to this small size, this offer high density active size for charge storage through surface redox processes. This enhanced specific capacity act as an active reaction center. Next, we'll see biomimetic materials and self-assembly. This biomimetic materials like cellulose, chitosan, silk fibronin, lignin, these have sparked the attention due to the inherent hierarchical structures, their environmental friendliness, and renewability. These contain the cellulose nanofibrils are scaffold for these are very flexible. These have porous carbon electrodes. Let's see the fabrication techniques. The first one is self-assembly. It uses natural molecular interactions such as hydrogen bonding, pi stacking, electrostatic interactions to form ordered and stable structures. It doesn't need any external template. It allows precise control of pore size and surface chemistry, enables uniform dispersion of active materials. The second thing is template directed synthesis. It utilizes natural or synthetic templates to create 3D porous frameworks with preserved geometry and porosity. This, for example of this, is wood templates. This can be carbonized into 3D scaffolds with vascular network channel networks. It supports high conductivity and mechanical toughness. From now, Rohan will continue.
So this is fabrication technique one. This is a template assisted synthesis. So this is the process. So this technique utilizes natural or synthetic templates to organize hierarchical porous structures in the electrodes. So sacrificial templates are used to deposit or grow materials on predefined architectures, and these are removed to generate interconnected pore networks. So this allows a natural, so we have the natural templates, which are wood, coral, diatoms, and this involves carbonization, where the templates are pyrolyzed to form conductive carbon structures. And we also have sacrificial removal. So the template removal is going to expose the 3D interconnected pores, and this allows for electrolyte mobility. So this provides performance enhancement. So the wood-derived carbon scaffold preserves the native vascular microchannels, supporting high surface area, improved electrolyte penetration, and mechanical toughness. So the electrodes fabricated using these methods are going to usually exhibit 5 times greater electrolyte infiltration compared to normal flat electrodes. So what we can see from this is there's 5 times higher electrolyte penetration. There is excellent surface area and pore connectivity, and there's going to be improved ion electron transport and mechanical integrity. So what is the challenge? The challenge is template heterogeneity. So the template guided fabrication requires accurate template selection and removal steps to prevent contamination and preserve structure. So natural templates like wood or coral, they may introduce heterogeneity in the material quality and structural uniformity. So what we can see here is there's natural variability. So for example, the wood grain or porosity. So what does this affect? This affects the structural reproducibility and the consistency in the electrochemical performance. So fabrication technique two. This is 3D printing or 3D printing bio-inspired electrodes. So this is wood grain or honeycomb patterns. So what's the method used? So the method used is additive manufacturing, or AM for short, and 3D printing. So this basically provides new possibilities for us to create highly tailored bio-inspired electrode geometry. So we get many shapes. So for example, direct link writing, stereolithography, and inkjet printing. So these are methods we can utilize. So these techniques allow preset control over porosity and composition, mimicking structures like wood or honeycomb. That's why it's utilized. So what are the achievements? So 3D printed electrodes have already demonstrated improved mass loading and mechanical flexibility, while also allowing them to produce complex structures and geometries such as honeycomb or wood grain. So basically, the fabrication of custom honeycomb or wood grain inspired architectures is what's been achieved. And this is given 40% higher mass loading compared to other traditional methods and enabled material efficient prototyping with minimal production waste. So, what are the limitations we can see here? So, one of them is the ink composition optimization. and we have resolution limitations along with post-processing demands. So what are the resolution constraints? So it limits the structure precision at the micro scale, which is obviously going to affect its performance. And next we have the ink formulation. So the ink must actually be able to balance flow, curing, conductivity, and stability. So for it to do all of those things, it's tough to design, and it requires ongoing material for rheology optimization. So fabrication technique three. So this is electrospinning and biopolymers. So what is electrospinning or nanofiber fabrication? So electrospinning is a generic approach to producing continuous nanofibers with variable diameters, and they have a huge surface area that resembles a fiber architecture of natural tissues, for example, collagen or plant cell walls. So it creates nanofiber mats with a high surface area, they're porous, and they have a flexible architecture. What does it enhance? It's going to enhance the ion conduction and the electrode electrolyte interface contact. So it basically electrospun carbon nanofibers doped with heteroatoms exhibit enhanced conductivity and electrochemical performance. So biopolymers for electrode design. So what is this? So natural biopolymers like cellulose, chitosan, or lignin are renewable resources for carbon-based materials with built-in porosity. So cellulose nanofibers, which are carbon aerogels. So they have high mechanical flexibility, tunable pore architecture, conductive carbon networks. So cellulose-based electrodes offer flexibility, pore control, and high rate battery for the high rate battery applications. So one of the main advantages is its sustainability. So it's a green method which is going to promote sustainability by utilizing the waste biomass, and we're going to obviously, while utilizing a renewable resource, reduce the fossil fuel consumption. So it uses agricultural or wood waste, and it leads to around 60% lower carbon footprint in electrode production compared to synthetic carbon sources. So electrochemical performance. So the key performance benefits or matrix are capacity retention. So electrodes inspired by bone or leaf veins maintain high porosity and structural integrity during repeated charge-discharge cycles. So there's greater than 90% capacity retention after even 1,000 cycles, more than that, in fact. So it sustains long-term electrochemical stability. Next is rate capability. So these bio-inspired porous structures allow uniform ion diffusion, and this is going to reduce the overpotentials and increase charge speed. So this has shown 5 times faster charging speed at high current rates. For example, 5 coulombs. Next, we have enabled rapid electrolyte infiltration and low ion transport resistance. So, and we have mechanical stability as the third point. So hierarchical frameworks buffer stress and prevent material breakdown during lithiation or delithiation. So there's 80% less volume expansion than conventional electrodes, and it reduces electrode pulverization and failure. So what is the synergistic effect? So the combination of hierarchical pores and conductive biomaterials enhance redox activity, ionic conductivity, and charge storage. So this includes the pore network, enhances ion transport, and the biomaterials which improve charge transfer and mechanical flexibility. So this is the first application, which is lithium-ion batteries or LIBs. So bio-inspired electrode designs for lithium-ion batteries. So first we have wood-derived carbon scaffolds. So the carbon scaffolds are made from wood and they have interconnected porosity, which provides excellent host for lithium storage materials. So there are a few points. So it mimics the natural vascular channels. It enables efficient lithium-ion transport, and it buffers volume changes during lithiation and delithiation, and it enhances the mechanical stability and also the electrolyte access. So next is the leaf vein inspired electrodes. So bio-inspired 3D electrodes modeled after leaf vein patterns improved rate capability and reduced local hotspots and distribute ion uniformly. That's how it's achieved that. So we have fractal vein network supports. So it provides even lithium ion distribution across the electrodes. It reduces the ion accumulation zones, which are nothing but the dead zones, and the faster or more uniform charge transfer. So what is the electrochemical output from this? So we have hierarchical structures from bio-inspired designs provide improved mass transport, capacity retention, and energy density. So it's basically achieved 20%, 25% higher energy density compared to the traditional graphite anodes, greater charge storage, volume, enhanced cycle life, and rate performance. From here, Sanju will.
The second application of bio-inspired electrode is on sodium-ion batteries. Sodium-ion batteries in the first cellulose-derived batteries. It has bio-inspired porous architectures made from natural polymers like cellulose, facilitate volume expansion and boost sodium-ion diffusion. It accommodates larger Na plus ionic radius and better structural changes during insertion or extraction. 92% capacity retention after 500 cycle, and also improve large term cycling stability. Honeycomb inspired anodes. Ele- electrode modeled after honeycomb architecture offers stability and electrochemical activity by combining high surface area and mechanical robustness. Hexagonal porous network, which gives faster ion transport and enhanced electrochemical performance, and delivers up to 300 mAh per G capacity. Stability advantages of this sodium ion batteries. Sodium is earth abundant and offer a more environmental friendly and cost effective alternative to lithium. Sodium is widely available and non-toxic, low cost. Combined with bio-driven carbon electrodes enables green battery production and reduce the environmental impact. So the third application of bio-inspired electrodes is on solid state and flexible batteries. A solid state battery is bone bone mimicking 3D porous carbon scaffold which support lithium metal anode by uniformly disappearing lithium ion and inhibiting uh, dendritary development. Bio-inspired 3D scaffolds like bone-like structures and which prevents lithium dendrite formation and maintains interfacial stability with solid electrolyte, and also architecture's 99% Coulombic efficiency in repeated cycle. And the next one is flexible and variable energy systems. Electroporous nanofiber mats that resembles spender silk or muscle fiber can be used as flexible electrode with high conductivity and tensile strength. The spiker silk-time nanofibers via electro spin and provide mechanical flexibility and also conductive networks, and also withstand 500 plus bending cycle without failure. And it is suitable for variable electronics and soft robotics. Let's see the challenges of bio-inspired electrodes. First one is scalability, like 3D print and template and synthesis or structure precision. They offer lack the cost, effectiveness, and throughput required for commercial manufacturing. These high-cost fabrication methods, such as 3D printing, electro spinning, and natural template variability, such as wood, coral, leads to inconsistent pore structure, which is 30% longer production time due to extra processing. Safety issue. Bioelectrode undergo cycling and collapse and to discharge cycle, and also biopolymers degradation, which undergo long-term electron exposure, electrolyte exposure. And third one is integration with emerging battery system. Integrating bio-inspired electron into solid state batteries require precision interface engineering, which is poor contact with solid electrolyte and risk of interfacial resistance and dendrimer formation if design isn't optimized. Uh, the future directions of this bio-inspired electron are: first one, AI-driven electrode design. We can build AI-driven electrode design like using AI ML algorithms, tools, and which can accelerate the discovery of hierarchical electrode structure with optimized performance. Use of AI ML or a model is to optimal pore architecture and components. It enables customized high efficiency design based on application needs. The second future application is smart functional material. The, the next wave of bioinspired system may include dynamic adaptive material, then the respond to damage or stress, uh, which is to development of self-healing electrode and materials mimicking biological tissues, which restore functionally after micro damage. And also it improves safety, cycle life, and battery longevity. Uh, the third one is green and sustainable materials. Utilization of architecture and industrial waste streams to develop zero toxic, low impact carbon electrodes in growing research direction, which converts waste mass into porous carbon material and which achieves non-toxic, low emission electrode production, and also supports circular economy principles. Fourth one is advanced characterization of techniques. In situ and operando techniques are vital to vital to understand long-term structure changes in bio-inspired electron. In situ microscopy and spectroscopy, which allows real-time observation of pore collapse, ion immigration, and material degradation. This advancement helps in optimized design and stability over time. So overall conclusion of this bioinspired electrode is uh, it is nature's design of a powerful solution to modern battery challenges. It helps to overcome the challenges which we are facing from the conventional batteries, and bioinspired electrode addresses limitations of conventional designs such as 40% higher energy density, and also it gives more than 90% capacity reduction over 1,000 plus cycles, and structural flexibility for variable and flexible devices. These bio-inspired electrodes enable faster ion transport and better mechanical stability, and also higher sustainability. So this is the overall conclusion of this bio-inspired electrode.
Thank you, sir.